Hello everyone and welcome to a new Unity scripting tutorial. And I've been getting some comments asking me to explain the math that I use in the tutorials that I've been making so far, but I didn't want to go in depth in these videos into the math just so that we don't get sidetracked away from the point of the video. So I wanted to make a series of videos covering the vector math that I've been using there, and if you find this helpful, let me know and I'll keep making them. And in this video is going to be an intro video to vectors. So we'll be covering how to create a vector, edit its components, add two vectors and subtract them. So the first thing that we need to create is a script to hold our vectors. So let's create a C# script called vectors and also create an empty game object to attach the script to. Now that it's created, we can open up our script. And to create a vector in Unity, we're going to be focusing on vector 3s, but keep in mind that a vector 2, all it is just a vector 3 where the z-axis zeroed out. So anything that you can do with a vector 3, you can do with a vector 2, or anything that you want to do for a vector 2, you can do with a vector 3 by setting the z component to 0. So let's create our vector 3 and call it mvec. And by default, vector 3s are set to 0 for the x, y, and z components. So to edit these components, however, what you can do is to say inside one of the functions, mvec.x equals, let's say, 2.5. And to see what's inside the vector, you can do debug.log and then pass it in the vector, so mvec. But before we do mvec.x, let's first debug.log what's inside the vector by default. So if we run this, as you can see, it's 0, 0, 0 by default. Now, if we have mvec .x equals 2.5, now the x component should be 2.5 and the rest will stay as 0. And of course, we can do the exact same thing for the .y and the .z. So this is one way to change the components of a vector. Another way to change the whole vector at once is to say mvec equals a new vector 3 of, let's say, 5.0, 2.0, and 4.7f. So this is creating a brand new vector and putting it into our mvec. Now if we run it, we should get the new values that we just got. So 5, 2, and 4.7. So this is how to create a vector and how to edit its components. Now let's move on to adding vectors together. And a really helpful way that I use to visualize what vectors are doing is to think of vectors as arrows instead of points in space. Like the issue is in Unity is that when you click on an object and you look at its transform, you'll see its position as an x, y, and z value. So it looks like it's describing a coordinate in space where it has x, y, and z. However, visualizing it just as a point becomes an issue if you're trying to, let's say, subtract two vectors together, or you're trying to scale a vector. So to explain this better, let's draw a 2D grid or a 2D Cartesian system here. So let's say we have our coordinates, and this is 0, 0, and 0. So this is a flat plane with 0 where the z is 0. And let's say we have a vector that's sitting right here, which is at, let's say, 5, 4, and 0. Now, thinking of the point just as a point in space doesn't do us a lot of good. But to think of it as an arrow starting from the origin, extending all the way to where the point is, makes it a lot easier to visualize and work with. And especially, let's say, for addition. Let's say you have two vectors that you want to add together. We have the 5, 4, and 0 vector, and let's say we have a vector that's pointing this way. So a vector pointing this way, or at this point right here, let's say it's at -1, 1, and 0. Now, to add vectors together, you just add the components to each other. So if we want to add these two vectors, we can add -1 to 5, which would give us 4. We can add 1 to 4, which will give us 5. And we can add 0 to 0, which will give us 0. And we end up with a vector of 4, 5, and 0. So this will be somewhere, let's say, this is 5 and 4, so we'll be somewhere here, somewhere down here, somewhere around here. Right? No, that doesn't make any sense because the y is 4. So it's going to be 4, 5, and 0. So somewhere around here. So that's 4, 5, and 0. So at the same time, you'll notice that the distance from the origin to where this vector is looks like it's the same as the distance from this point to where this is. And this is exactly it, is that to add two vectors together, you just take one of the vectors, and the tip of the vector is where it ends, and the tail of the vector is where it starts. So you can go to the tip of one vector and take the other vector and start it from there and extend it to where it needs to be, or where it should go from the origin. So that's where it extends, and you'll notice that this is parallel to this. They have the same length, and this is our 4, 5, and 0, which is adding the two vectors together. Now, if you're adding, let's say, this vector to this vector, this is what you do. But if you're adding this vector to that vector, what you can do is to just start from here and then add this vector right here to it. And you'll end up with the same result. And if we do the math, we can do, so when we first started, we said -1 plus 5. If we go the other way around and say 5 minus 1, we still get a 4. 4 plus 1, we still get a 5. And 0 plus 0, we still get a 0. So it doesn't matter if you add the first vector to the second or add the second vector to the first, you end up with the same result for vector addition. And we can verify this by creating another vector in Unity. So vector 3, let's call it vec2, equals, let's say, new vector 3 of, let's say, use the same vectors that we used here. So -1, 0.0, 1.0, and 0.0. And let's edit our first vector to be, we have 5.0, 4.0, and 0.0. Now, if we do mvec plus vec2, and this is how you add two vectors together in Unity, and run it, we get 4, 5, and 0, just like we got here. Now, if we do vec2 plus vec, we should get the exact same result. So if we stop this and then run it again, we get the exact same result. So, and this is a really great way to visualize what vectors are doing, because let's say you want to, let's delete this for a second, right here. Actually, let's keep it for now. Let's say you added this vector to this vector and you ended up with this vector right here. Now your new vector is starting from the origin and extending out to your new point. And then if you add another -1, 1, and 0 to it, it'll go for another starting from the tip, going to the same distance, and this is your new vector. And it's almost like you have a starting position and you keep adding the same distance to it over and over again. It's almost like you're adding a speed or a velocity vector to your object. So if your object starts here and you're adding a velocity to it, it just keeps going in the same direction by a certain amount according to the other vector. And this is what's really good about vector addition. So let's try to actually apply this. Let's create a 3D object, let's say a cube, and let's start the cube at, let's say, 5, what is it, 4 and 0. There we go. And then let's create a public transform in our script to attach the cube to. So we'll call it object, so obj. And then in update, we can say object.position equals. So over here, we said that our position is, we take our current position and add the next vector or the addition vector to it. So we can say object.position. Let's call this one, let's assign actually this one to mvec, because we have access to mvec over here. So our mvec now is -1, 0, and 1, which is this vector right here. And we can say object.position equals object.position, so mobj.position plus mvec times time.delta time. And time.delta time is just a scale factor. We'll cover scaling later. But for now, it's almost like we're adding this vector every second. Now, if we run it, we need to attach the cube to the script. And then if we run it, there we go. As you can see, it's moving up in the same direction that we have here. So it's moving up in the same direction because we're taking our position and adding our vector to it over and over again. Now, an easy way to add this instead of saying object.position equals object.position is to just say object plus equals mvec times that, and it just takes whatever the position and adds the vector to it. So this will give us the exact same result as the first one. There we go. And that covers object or vector addition. Now, vector subtraction is a little different. For vector subtraction, let's say we have two vectors, just like the ones that we have here. Now, to subtract the vectors, the order matters, unlike addition. Because, for example, let's say we want to take 5, 4, and 0 and subtract -1, 1, and 0 from it. So we can do -1, 1, and 0. Now, we do the component by component subtraction, just like the addition. So 5 minus -1 would be 5 plus 1, so we would get 6. 4 minus 1 would be a 3, and 0 minus 0 would be 0. Now, if we do it the other way around and start with this and subtract the 5, 4, 0 from it, we'd end up with -1 minus 5, which would give us -6. 1 minus 4 would give us -3. And 0 minus 0 would give us 0. So as you can see, the order of the vector, the order that you subtract vectors in matters. But you'll notice that one vector is just the negative of another vector. And that will make sense in a second, because it is pretty helpful to know that, that they are basically the same vector, it's just the signs are flipped. So a really nice way to visualize how vector subtraction works is that, like we said earlier, you have the tip of a vector and a tail of a vector. So the tip of a vector is where it ends and the tail is where it starts. Now let's say we're starting with 5, 4, and 0 and subtracting -1, 1, and 0 from it. Now you can think of this as a vector that is ending at 5, 4, and 0 and is starting at -1, 1, and 0. And this is the direction of the vector. However, it's not actually starting here and ending there. It's starting from the origin and going parallel to that vector that we just drew. So this is our actual result, which is 6, 3, and 0. And then if you subtract it the other way around, it would be, instead of starting from here and extending out, it would be starting from here and extending towards the other way around, which would be somewhere from the origin extending down. So let's put this into practice and create two cubes. So let's say we have two cubes now. We have cube 1 and 2, and let's create a public variable for it. Let's call it object 2 and attach our objects to the script. So we have object 1 and 2, and let's say we want to, let's say we have this one at 5, 4, and 0. Let's put this one at -1, 1, and 0. So that's where our 2 points in space were before. And now let's first debug.log object 1 dot position minus object2 dot position. So we're taking the first position, which is 5, 4, and 0, and subtracting -1, 1, and 0 from it. And let's see what we get. So we get our 6, 3, and 0, just like we got here. Now, if we flip the two and did object2 dot position minus object dot position, we get the same vector but with every component negated. So it's flipped in the opposite direction. And subtraction is really helpful when you want an object to move towards another object. So let's say we want object 1 to move towards object 2. Now we know that if we have object 1 at 5, 4, and 0, and to make it move towards object 2, we need to take object 2 position and then subtract object 1 position from it. So we're going to take -1, 1, and 0 and subtract 5, 4, and 0 from it. And that will give us the direction that we need to go. So we can say vector 3. Let's create a vector here called direction. And in start, we can say direction equals object 2 minus object 1 position. And then in update, we can say object dot translate by the direction times time dot delta time. So let's remove the object position plus equals. So we're translating our object in the direction that we just calculated here. And let's see what happens in this case. As you can see, object 1 starts here and then it moves towards object's 2 direction. If we want to flip it the other way around, we can say the direction is object minus object 2 and then translate object 2 instead. That will make object 2 go towards object 1 instead. And that can work no matter where object 1 is and no matter where object 2 is. It will always go towards where object 1 is. Keep in mind though that this is just a direction. So let's say we have a public object 3 and let's make a new cube and attach it to our script. There we go. And let's set the new cube's position to 0, 0, 0, or even over here. Let's set it over here. Now, if we do the same thing with object 3 and translate it in that same direction, you'll notice that it's moving in the general direction as object 2, but it's not actually going towards object 1. Because as we said here, the subtraction doesn't actually give you the vector from one to the other. It gives you a vector from the origin pointing in the direction where it needs to go. So our starting point, the place we need to start at, is our actual position. And this is why when we subtract object 2 from object 1, we need to translate object 2. So this is it for addition and subtraction. I know it was pretty in-depth for a pretty basic subject, but I like to kind of really explain what a thing does to get a better understanding of it, and especially visualizing it helps me a lot, so I hope that it helped you as well. If you have any questions, suggestions, or feedback, please leave them below. Otherwise, thank you very much for watching, and I will see you in the next video.